Algorithms solve problems. At the conclusion of this lesson, you will be able to explain the formal definitions of a problem, an algorithm, sequencing, selection, and iteration. You will be able to explain that some problems may look different, but be similar, or look similar, but be different. You'll also be able to explain that some algorithms may look or operate differently, but will still solve the same problem. This is the first lesson in Unit 6, and many of you will be doing this online as your homework after the Unit 5 test. Now, as a prompt, think about this. What makes two pieces of code the same? Could there ever be two pieces of code that you consider to be the same, even if they aren't identical? Some of you may be saying, well, if it does the same thing, it's the same code. Others say, nope, it's got to do it the exact same way. It's got to have the exact same commands, exact same comments. A lot of things can mean the same. What do we mean by the same? You should think about that as we continue on. Now, what I'd like for you to do as you're watching this video, since we are not in the classroom for this, is to jot down how you would find the answer to these 10 problems. So just, you don't have to write down the problem, you can write down this is what I do, this is what I do. 1, find a person whose birthday is before yours, and 2, find a person whose birthday is after yours. 3, find the person whose birthday is the closest before yours. 4, find the person whose birthday is the closest after yours. I lost count. 6, find the person whose birthday is closest to yours. 7, find the person with an equal number of birthdays before and after theirs. Find the 2 people with the closest birthdays in the room. Find the shortest period of time in which 3 people have birthdays. Find the shortest period of time in which 4 people have birthdays. Find the longest period of time in which no one has a birthday. So there's 10 problems. Jot down, how would you go about, if you could walk around the room, how would you go about solving all of these problems? How did you or would you go about solving each of these problems? Which problems did you need to do something similar in order to solve? Well, if we look at it, problems 1 and 2 are very similar. As soon as you find one person who meets the criteria, you know you're done. Problems 3 and 4 are very similar, but you need to talk to every other student to answer it. You only need to keep track of the closest birthday you've heard so far, however. Problem 5 is easy to solve as soon as you've solved problems 3 and 4. As soon as you've got 3 and 4 done, you know which one, before, after, or on your birthday, is the closest. Problems 6 through 10 require you to have written down everyone's birthday, likely in order. Problems 7 through 9 are the same problem for different numbers of people. Whatever strategy you use for one of those would be helpful to solve the others. Problem 10 is a different creature, different version of problem 7. But instead of finding the smallest gap, you're finding the largest. So notice there's similarities and there's differences. Now, the first thing that we need to think about as computer scientists is, what is a problem? We just looked at 10 problems, but as we discussed, a lot of them are similar. If we solve one problem, we may actually solve another, or at least have a good idea of how to start solving another. As computer scientists, it's important to ask, have I seen this problem before, or how is this problem similar to others I've solved? We just thought about whether problems are similar. Now, we're going to look at whether we're actually solving the same problem. What you need to do is access the handout. It's on the Canvas page. It says, which of these algorithms are the same, or which algorithms are the same? You want to either have that printed out or bring it up on your computer so you can look at it during this next activity. What I want you to do is look at these different algorithms. There's 6 of them, and sometimes on the paper you can sort of spread it out or write down. Well, look at algorithm 1, 2, 3, 4, 5, and 6. And you want to tell me which of these algorithms are the same and why. What makes it the same? What is your criteria for being the same? So again, pause the video. I don't know if you can get all of it in here or not. I guess not. So you're going to have to look at it on the paper, okay? But you can look at all 6. So pause the video, go pull up the page, and figure out which of these algorithms are the same. Okay, now you're back. Well, did you decide which algorithms are the same and why? What's your definition of the same? Well, algorithms 1, 3, and 4 draw a square, while 2, 5, and 6 draw a rectangle. You could say those are the same. 1, 3, and 4, and 2, 5, and 6. However, algorithms 4 and 6 are written using a flowchart, while 1, 2, 3, and 5 are written in the AP pseudocode. So maybe that's what makes them the same. Some of these algorithms turn the robot right by turning left 3 times. It's debatable whether we can really call these algorithms the same, because the robot's basically turning. If it was a dance move, there's a big difference between turning to the right and turning to the left 270 degrees, right? Some of these algorithms create lists or variables to store information. Depending on the context, we may not be able to call these algorithms the same. So wrap up. A problem is a general description of a task that can or cannot be solved with an algorithm. An algorithm is a finite set of instructions that accomplish a task. There are usually many algorithms to solve the same problem and many ways to write or express one algorithm, including natural language, pseudocode, diagrams, and are implemented using programming code. All algorithms can be created by combining steps in 3 different ways. Sequencing, that's where you put one step in front of the other. Step 1, step 2, step 3. There's selection. You decide which step to do next based on some condition. If the condition is true, you do one step. If it's false, you do the other step. And then there's iteration. There's doing some steps over and over and over and over until the condition is met. Again, once the condition is met, you start doing that process. You check the condition again and again and again, and when the condition is finally false, you exit the loop or the iteration. Now, how did today's activities change the way you think about algorithms and problems? Well, computer scientists don't just think about code. They think about problems and the algorithms that solve them. In this unit, we're going to explore what makes 2 problems or 2 algorithms similar or different from one another, and the way computer scientists talk about them. Not only will you be a better programmer, but you'll get to work on some really interesting problems along the way.